Hello, my name is Satyavrata Samavedi. I'm a faculty member in chemical engineering at IIT Hyderabad. My research lab at IIT Hyderabad works in the broad domains of polymeric biomaterials and pharmaceutical soft matter. Essentially, we're interested in understanding how processing of polymers affects their structure property relationships, and then using this understanding to deploy polymeric biomaterials in pharmaceutical applications, particularly the design of amorphous drug formulations, as well as designing controlled release drug carriers based on polymers, which can provide controlled release of small molecule drugs and biotherapeutics. And I'm absolutely thrilled to be announcing a course on the NPTEL platform that I will be offering, titled Polymeric Biomaterials, Structure, Properties, Function and Performance. And in this short introductory video, what we will do is to provide you with an overview of what this course is going to involve, the topics that we will cover as part of this course, the guiding philosophy behind the course, whether this course is right for you or not, and if you end up taking this course, what can you hope to learn. Now, most of you watching this video would have heard of polymers and be familiar with polymers in some context or the other, because polymers are just ubiquitous. They are all around us, right from within us in the form of proteins or polysaccharides. Essentially, these are long chain molecules, to everyday objects around us such as polyethylene bags, PET bottles, polypropylene containers, polyurethane foam cushions. The list is just endless. If you just do a quick scan of the rooms in your house, you will find likely that the wire casings in your home are most likely polyethylene, which is a polymer. The non-stick coatings that are used in your kitchenware are polymers. The windows, glass windows, are most likely not glass in your home, but more likely plexiglass, which is a polymer. The wooden cabinets where you keep your books, that's made from a natural polymer cellulose. And even something as inconspicuous as the bristles in your toothbrush in the bathroom are a polymer, nylon. Now, would you believe it if I told you that all these polymers that I have just listed so far are also biomedically and clinically important? That you are a bit intrigued to know how industrially important high performance materials have been engineered, designed and used for sensitive applications in the biomedical industry. Indeed, today polymers form the foundation and basis for a wide variety of applications driving innovations in the healthcare domain. Now, polymers are used in a lot of different diverse and versatile applications, including as liners in hip or knee implants. Polymers could be used as coatings and drug-eluting stents. They could be used as dental composites in your fillings. Polymers could also be used as sutures in surgery. They could be used as scaffolds for tissue engineering. They can be used as drug carriers for controlled release applications, or even as excipients in pharmaceutical formulations. They can be used in the design of diagnostic platforms and microfluidic devices. The list is just endless. But what you will notice here is the broad canvas of properties that polymers can show, just based on the applications I've just talked about. What is remarkable though is, despite having such a large versatility and diversity in properties, there is a common structure property function framework that guides the engineering, design and use of polymers across all these applications. And the focus of this course is going to be looking at that paradigm, where we are going to primarily be looking at studying how structure affects properties and how processing affects structure property relationships, and how all of these together jointly dictate the end use and performance of polymers in various biomedical applications. And we will do this with a special focus on two very unique aspects of polymers, namely hierarchy, both in structural organization as well as multi-scale functionality. So, the primary objective of this course is to blend or to connect fundamental concepts in polymer science and engineering with real world applications in the clinic and in biomedical engineering, essentially bridging theory with practice. And from a design or an engineering perspective, we're also going to be interested in studying the properties of polymers and benchmarking them and asking questions such as, if I have a specific application in mind and there is a particular functionality required, can I backtrack and ask what kind of properties are required for that application and that functionality, and in turn what kind of structure should the polymer have, and in turn how is the polymer processed and designed. So essentially looking at design principles that guide the use of polymeric biomaterials in many of these applications. And we will be doing this by looking at numerous examples of clinically important polymers, biomedical polymers, both synthetic and natural, examples of scaffolds, hydrogels, implant components, and so on. And all of this will be contextualized throughout the course against the backdrop of key applications such as drug delivery, tissue engineering, regenerative medicine, diagnostics, as well as prosthetics. I want to take a minute to talk to you about a couple of very exciting and interesting aspects that actually make this course unique. The first one is our particular focus on a conceptual or a physical understanding of especially tricky or slippery ideas. So we will pay a lot of attention to detail in this course to clarify some of these concepts. For example, definitions. You can talk about biocompatibility. That's a word that's commonly used in everyday language, and you will see this in the literature as well. But does it really mean what we think it means? That's something that we're going to clarify in this course. You can also ask to be cleared by a federal agency such as the FDA. Is that the same as being approved? So is FDA cleared the same as FDA approved? And then you can also ask questions like, does FDA clear or approve polymers, or does it approve or clear polymers as part of a device in a specific application? So these are all concepts that we will look at in quite some detail and clarify. And this is also true from the polymer side of things. We're also going to be looking at words such as toughness and hardness from a performance perspective. These are words that we use in our everyday life, but in an engineering context, they mean very specific things, and we will focus quite a bit on understanding conceptually what those words mean. Something as tricky as glass transition temperature, for example, right? That's a physiologically very, very important property for polymers that needs to be accounted for when you design polymeric biomaterials. And from a thermodynamic perspective, you can ask, is this a true second order transition? Some textbooks will call it a pseudo second order transition. What is pseudo about it? So all these kinds of tricky, slippery ideas that might be a bit blurry, we will try and focus on with special attention and clarify them to provide a good conceptual understanding. The second aspect of this course, you will see throughout the lectures these orange boxes popping up on your screen, and they will serve one of three purposes. The first is pause and recall value. Essentially, all the lectures in this course are designed to be reasonably standalone. So you can walk into one lecture and get most concepts out of it if you have some understanding of polymers. But if you are taking this course from the beginning, then we will build into more advanced topics as we proceed through the course. And as we do that, we will refer back to concepts that we have seen in earlier lectures, and these pause and recall orange boxes are meant to connect the dots for you and help jog your memory. The other reason why we might use the orange boxes is for pause and look up. Essentially, we might have built a very strong foundation for certain concepts in the course, but we may not have had a chance to look at some of the more advanced, more contemporary aspects of those concepts. So we will use these pause and look up orange boxes to point you to some more reading outside of the class, which you should be able to pick up on your own. And the last one for which we will use the orange boxes is for pause and reflect. These are some high points in the course, particularly when we have structure property function relationships. We will stop and look at some quick examples or case studies, and the idea here is to emphasize and strengthen your conceptual understanding through these pause and reflect boxes. And another very exciting, personally for me, one of the most fulfilling and exciting aspects in designing and offering this course is we are going to be looking at all of this science, but through the eyes of the scientists who contributed to this field. Shown on your screen are some just examples of just some of these scientists whose contributions we will look at, But we will not just stop at looking at the scientific contributions. We will go a bit deeper into history and try and ask if we can learn something from their lives, their passion for science, the difficult times through which they lived, and yet not giving up their pursuit of science. What was their approach to science? So can we learn some lessons from their lives and their approach to science apart from appreciating their scientific contributions? More formally, this course is spread across 12 weeks and will consist of 30 to 35 lectures. In week 1, we will set the tone by looking at basic definitions that are required for the course, some historical perspectives, and how biomaterials are used as part of devices. Weeks 2 and 3 will focus on structure property relationships, essentially fundamental concepts in polymer science. And weeks 4 and 5 will then move to temperature and solvent effects, which are both important not just from a polymer microstructure perspective, but also to understand polymer processing, and also because temperature and solvent will both play a very important role in eventually dictating the performance of polymeric biomaterials under physiological conditions. And using the basis or the foundation that we have laid very strongly in the first 5 weeks, weeks 6 and 7, we will now look at specific examples of clinically important biomedical polymers, both synthetic and natural. We will also look at hydrogels. We will look at numerous examples of these to help strengthen the idea or the paradigm of structure property function relationships. Weeks 8 and 9 will look at the bulk. We will be looking at bulk mechanical properties, mechanical testing, what properties are important for specific physiological applications. We will also look at concepts related to viscoelasticity. Then week 10 will move to processing, and here we will look at how processing again can affect structure property function relationships. We will also do some demonstrations where our lab has some expertise in that area. Week 11 will move on to surfaces and surface interactions between the biomaterial and the host, starting off with proteins, protein adsorption, and then biological interactions. And eventually in week 12, we will tie all the concepts we have seen in this course together by looking at biomaterial performance as part of translation. We will also look at some practical aspects related to regulatory affairs. This course is meant to be self-contained in that all the concepts you will need will be provided as part of the lectures, but we have drawn inspiration from some particular reference textbooks which are being shown on the screen right now. So depending on your orientation, depending on what your interest is, if you are interested in additional reading, these will serve as good repositories for you to go look up more details beyond the scope of this course. And while these 5 textbooks that I have mentioned are not exhaustive, they are meant to have broad scope in that some of them will have a more biomaterial focus, some of them will have a more polymer focus, some of them will have a more engineering focus, and depending on the flavor that you are interested in, you can look up some of these textbooks. So whether you are an undergraduate, master's or a doctoral researcher who is exploring this domain or who is working actively on this domain in research, or if you are an industry practitioner working in the chemical, polymer or biomedical or pharma or healthcare or implant domains, or if you are just plain curious about how polymers drive innovations in healthcare, this course is designed for you. The only prerequisites that we will require are some basic foundational college level first year courses in physics, math and chemistry that most of you would have done. Apart from that, we are not going to make any assumptions about your knowledge of polymers. You will start from scratch in week 1 and build all the way up to week 12 throughout this course. I hope you found this video exciting, and if you want to learn more about polymers and how they drive innovations in healthcare, please join me on this journey. I look forward to seeing many of you in the course.